voltage control of a single phase inverter. In many industrial applications, it is often required to control the output voltage of the inverter to cope up with the variation of DC input for voltage regulation for the constant voltage by frequency control. There are various techniques to vary the inverter gain. The most effective method of controlling the gain and output voltage is pulse width modulation control within the inverter. The commonly used techniques are single pulse width modulation, second multiple pulse width modulation is also known as uniform pulse width modulation, third one sinusoidal pulse width modulation, fourth one modified sinusoidal pulse width modulation, and finally phase displacement control. Let us see techniques one by one. So first we'll discuss about the single pulse width modulation and multiple pulse width modulation, sinusoidal pulse width modulation, modified sinusoidal pulse width modulation, phase displacement control. Multiple pulse width modulation. The harmonic content can be reduced by using several pulses in each half cycle of output voltage. The generation of gating signals for turning on and off the transistors are as shown here. Here also the carrier signal is a triangular signal, whereas the reference signal is a rectangular signal. The frequency of reference signal sets the output frequency F0 and the carrier frequency Fc. Determines the number of pulses per half cycle P. Now, the modulation index controls the output voltage. This type of modulation is also known as uniform pulse width modulation, that is UPWM. The number of pulses per half cycle is found that P equals to Fc divided by 2 F0, that equals to MF by 2, where MF is equals to Fc divided by F0 is defined as frequency modulation ratio, where Fc is the carrier signal frequency, F0 is the output frequency. The variation of modulation index M from 0 to 1, which varies pulse width from 0 to pi by P, and the output voltage from 0 to Vs. The output voltage of a single bridge inverter for uniform pulse width modulation is as shown here. This is an output voltage V0. If delta is the width of each pulse, then the RMS voltage V0 equals to 2P by 2 pi integral pi by P minus alpha divided by 2 pi by P plus alpha divided by 2 of Vs square d omega t under the square root. Then V0 equals to Vs of square root of P delta divided by pi, RMS output voltage. Now, from the Fourier series, the instantaneous output voltage V0 of t equals to sigma n 135 up to infinity Bn sin n omega t. Now, the value of Bn coefficient can be determined by considering a pair of pulses such that the positive pulse of duration delta starts at omega t equals to alpha, and the negative pulse of the same width starts at omega t equals to pi plus alpha. The effect of all pulses can be combined together to form the effective output voltage. If the positive pulse of nth pair starts at omega t equals to alpha m, then n set omega t equals to pi plus alpha m. Now, the Fourier coefficient for the pair of pulses Bn equals to 1 by pi of integral alpha m to pi plus alpha m cos n omega t d omega t minus pi plus alpha m to pi plus alpha m plus delta. This is alpha m plus delta cos n omega t d omega t. This value equals to 2 Vs by n pi sine n delta by 2 of sine n of alpha m plus delta by 2 minus sine of n of pi plus alpha m plus delta by 2. Now, Bn can be found by adding the effects of all the pulses. So, sigma m equals to 1 to p of the Bn. This is our Bn value. Now, if you observe the variation of modulation index for 5 pulses per half cycle, the order of harmonics is the same as the single pulse modulation. The distortion factor is reduced significantly compared to that of the single pulse modulation. However, due to the large number of switching on and off processes of power transistor, the switching losses would be increased. With large value of P, the amplitude of lower order harmonics would be lower, but the amplitude of some higher order harmonics would increase. However, such higher order harmonics produces negligible ripple or can easily be filtered out.